All right, this is lesson 8.1. We're introducing trig identities in this lesson here. We're going to talk about some fundamentals of trig identities, and then we'll use those in later lessons to factor and actually solve equations using some of these trig identities. So the basic trig identities come from the Pythagorean theorem, and the first value is sine squared theta plus cosine squared theta equals 1. And like I said, this comes right out of the Pythagorean theorem. And so from the Pythagorean theorem, of course, you remember, is you have a squared plus b squared equals c squared, which c squared, of course, is the hypotenuse length squared. And then a and b are the side lengths on the other side. So if I have this angle theta here, then the opposite side, instead of calling that A, let's call that O. And the B side here is my adjacent side. So I'm going to use a capital A so we don't confuse that. So that B side is A. And then C is my hypotenuse, right? So I'm going to put an H there for that. So rewriting this equation then, I would have A squared is going to be O squared, our opposite side squared, plus the adjacent side squared, equals the hypotenuse squared. Now, what else could I do to this? Well, if I wanted to, I could divide both sides of this equation by h squared. Okay, so h squared here, and then this whole thing is divided by h squared. And if I break this out, I would have O squared over h squared plus a squared over h squared. And then h divided by h squared is 1, right? H squared divided by h squared. So this is just 1. Well, if you'll remember that our sine function is opposite over hypotenuse. And cosine is adjacent over hypotenuse. I'm not going to write that out. And so sine squared then would be O squared over h squared, right? So this really is just sine squared theta plus cosine squared theta equals 1. So that's where this whole Pythagorean identity comes from, and this is why we call them the Pythagorean identities. Now, there's a couple of other things I could do to these. So taking just sine squared theta and plus cosine squared theta. And if I divided this whole thing by, let's say, sine squared. Okay, so sine squared here, sine squared here. Probably should have done cosine first, but that's okay. And then this would be 1 over sine squared. So what does this equal? This is 1. And then this would be what? Cosine over sine is cotangent, right? So 1 plus cotangent squared theta equals, and then what's 1 over sine squared? Well, sine is cosecant, right? So this would be cosecant, CSC squared theta. Okay, there's a theta in each of these. And then the other way I could do is if I divided these things by cosine instead, I'd end up with sine over cosine, which is tangent squared theta. And then plus 1 equals, and then be 1 over cosine squared, which is secant squared. And so that's where these identities come from here. So these are your fundamental trig identities using the Pythagorean theorem. And then you could rewrite these in a number of different ways. For example, if I switch sides with this, right? If I added cosine to both sides and subtracted sine, I'd get 1 minus sine squared theta. Now, I'm not going to take the time in class right now to complete this whole thing. This is the table showing all of those different values in here. And I will post this on Canvas. I think I may have already, but if I haven't, I will post it on Canvas today. And you could see all of these different values. So don't feel like you got to fill this in right now. But I do want to highlight that one at the very bottom with a little arrow I got next to it is if I took everything times -1, you get that equation right there where I get negative sine squared theta minus cosine squared theta equals -1. So now using these Pythagorean identities, I can use them to simplify a number of different equations. So let's just start with tangent x and cosec times cosecant x. Well, tangent x is just sine x over cosine x. And then cosecant x is 1 over sine x. So in this case here, my sine x's cancel each other out, and you end up with 1 over cosine, which is, of course, secant x. Okay, so here, obviously that last one didn't have any identities in it other than the trig functions, but right in here I've got 1 minus cosine squared theta. Well, if you look at the trig identity list, we know that that equals sine squared theta, or sine squared x in this case. So sine squared x. And then cosecant is 1 over sine x, right? So this is 1 over sine x. And again, this is a multiplication problem. So with sine squared theta divided by sine, or sine squared x, I'm sorry, divided by sine x, of course, equals just sine x. Now, this is a good chance for me to kind of explain one thing. Remember in regular factoring and regular multiplication and stuff, we took a value like x squared times 1 over x. And that x being a variable means it could represent anything, okay? And in this case here, x squared is just sine squared x, right? So this x is sine, x equals sine x. And so this is no different than something that you've done before. It just looks a little different because I've got a sine and a cosine and tangents in here. But at the end of the day, if you just treated this as if this was x squared and this was 1 over x, then having that equal x is no big deal to you, right? We've done that 100 times. And so in this case here, my sine squared x divided by sine x is just plain sine x. Now, this is something a little bit different in here. Let me explain real quick. If I go and I drew a quick graph, in fact, rather than me drawing a graph of this, let's pull up Desmos, because I worked this on Desmos yesterday, and so I already have a graph ready. Okay. Okay, so in here, if I have my graph of cosine x, okay, so this red is cosine, and cosine starts at x equals, at 0, cosine is 1, because that's your cosine, if you remember on your unit circle, cosine is the x value. And so if I took that cosine and I shifted it to the right, pi over 2, it would look like that. Okay, so the blue is now the pi over 2 minus x function, okay? But I want to show you, I'm going to go ahead and hide that red. Okay, so this is my new shifted to the right function of cosine x. And like I said, this is right pi over 2. Well, if I put a sine function in here, see it turn green? It's the exact same function because at pi over 2, if you remember, our peaks and valleys occurred in intervals of pi over 2, right? It was pi over 2, pi, 3 pi over 2, and then 2 pi. And so shifting this thing one of my spaces to the right here, pi over 2, instead of being at 0 where sine would be, my sine function would the same way get shifted to the right one. So what I'm trying to say is that by taking that pi over 2 minus x and shifting it one of our intervals over to the right, then what we do is we turn sine into cosine and cosine into sine, okay, end of the day. So better than me trying to show you that graphically. So in other words, if you see this pi over 2 minus x, then all we've done is we shifted sine to the right 90 degrees, which makes it cosine. Okay, so this is now cosine x over sine x, which of course equals cotangent. Okay. Now, I could distribute these guys as well, but rather than distribute this, what we're going to go ahead and do is take the secant squared x minus 1. That is one of my identities. Okay, secant squared x minus 1 is tangent squared x. So this one here is tangent squared x. And this is still cosine squared x. So tangent being sine over cosine, then I have cosine squared x, and then times sine squared x cosine squared x. So in here I cancel my cosines out, and you're just left with sine squared x. All right, so here, again, I'm not using an identity, but I'm going to stick with just the, at least not a Pythagorean identity. But the cotangent is defined as cosine over sine. And secant, of course, is 1 over cosine. And again, these cosine x's cancel, and I'm left with 1 over sine x, which is cosecant x. So try to simplify these down as far as you can go. All right, 2 more examples. So cosine squared, and then this is that pi over 2 minus x, right? So this turns this whole thing into sine squared x over cosine x. And what I could do is break this up into 2 multiplication problems, right? I have sine x over cosine x times sine x. Sine over cosine x, this is tangent, right? So this would equal tangent times sine x. And I don't think I can take that any further than that. Let's go ahead and try. All right, so sine x over tangent x. Remember that tangent x being sine over cosine, but it's in my denominator. And I could take this tangent x out of the denominator and turn this into a multiplication problem. So I end up with sine x, and then tangent is sine over cosine, so inverting that, I'm going to flip this because my tangent is in the denominator, right? So this is going to be cosine over sine. And my sines cancel, and I'm just left with cosine x. All right, let's get something just a little bit more complicated because I want you to see how in-depth you can get with these. So 1 plus cotangent squared x is actually cosecant squared x. Right from my identities, okay? And then tangent squared x, I'm not going to touch that at this time. And then tangent minus secant squared x actually equals -1. Now what can I do with this? Well, let's go ahead and break these guys down into cosecant, of course, is 1 over sine. So this is 1 over sine squared x. Tangent is sine squared over cosine squared. And this whole thing's times -1. So I'm just going to put that over here as negative. So these cancel out, and I'm left with 1 over cosine squared x, which is secant squared x, and it's negative. So let's just call that negative secant squared x. And there should be an x here and here as a typo. I'll fix that later. Okay, that is it for this lesson.